Hi guys, good morning. It's another lovely Tuesday, and today we're going to be discussing physics. Okay, but before that, I want us to talk about somebody today, and we're going to see some fun facts about that person. Okay, so let's start by I'll show you the picture first of all. So, who is this woman? 3, 2, 1, guess. Who is this woman? She's very popular. I'm sure almost all of us should be able to get the answer here. This is a popular one. So I guess you would have said your answers by now. So let me just tell you who the woman is. Her name is Marie Curie. Marie Curie. Okay, if you want to pronounce it, the should I say English way. So yeah, that's Marie Curie, and she was a physicist, she was a chemist, she was so many things. She was a scientist, and we're going to talk about some of the things that she did and who she was, her accomplishments, and some other things today. So let's quickly go into that. First of all, we'll start with this very important fact. She was the first woman to win a Nobel Prize. Okay, so we talked about another woman in the previous lesson. I hope you've not forgotten, Amélie de Châtelet. Yeah, so this woman, Marie Curie, was the first woman to actually win a Nobel Prize. I don't know if you've heard about Nobel Prize. I think I've talked about that previously also. It's given in different fields, and sometimes physics, chemistry. Like I said in the last class, that you could also win one, if you have something very good to offer, and I think that's true. Yeah, you do. So let's just continue. So yeah, she was the first woman to win a Nobel Prize. Now, not just that, get this. She was the first person, get this, and the only woman to win a Nobel Prize 2 times. Wow. Can we clap? Yeah, you can clap. So she was the first person and the only woman to win a Nobel Prize 2 times. Okay, then she was also drum roll, she was also the only person to win the Nobel Prize in 2 scientific fields. How cool is that? How cool is that? Physics and chemistry. This woman was just a genius. She was simply a genius. And yeah, some of us actually are geniuses in one field or the other. Yeah, so you could just put in your best, and you never can tell. So this is just the beginning of what we're going to talk about. So let's continue. Now, do you know that she was also the first woman to become a professor in the University of at the University of Paris? Yeah, that's in France. Now, for physics, let's talk about physics. Okay, we talked about how she won 2 Nobel Prizes for physics and chemistry. Okay, now for physics, she was working with her husband and another scientist, which we call Henry. Yeah, another scientist. So the 3 of them actually worked together, and they developed now what you know today as radioactivity. You should be thanking these 3 people. Anytime you hear radioactivity, radiology, anything that has to do with radiology in general, when you hear anything radiology or radioactivity, you should be thanking these people. Yeah, so she was among the 3 of them, and they pioneered the work on radioactivity, and that was actually a word that she coined. They coined that word, radioactivity. Then for chemistry, she won the Nobel Prize for the discovery of 2 elements. So when you hear polonium or radium, just think Marie Curie. Yeah, she was the one that made, or let me not say demade, she was the one that discovered. She was the one that discovered those 2 elements. Isn't it wonderful? Isn't it wonderful? It's wonderful. She has contributed so much. Now, the effects of her work in physics and chemistry have had such a ripple effect over the years that we can't even should I say overemphasize what she has done. It's amazing. And I'm looking out for some of us that will actually do something so amazing. Yeah, we can. So I want us to just go on to talk about some other things that I want us to know. Now, when I'm just going to give you two examples, because if I want to really sit down and explain the radioactivity, explain everything it's used for, every field it's applied in, we're going to sleep here, because it's applied in medical field, it's applied in so many things, even in society as a whole. So her work is the applications of her work are endless, but I'm just going to give you two good examples. So look at this. The first one is an electron microscope. I think we all know what a microscope is. Yeah, it's used to see very tiny objects that you might not be able to see with your physical eyes, or sorry, not your bare eyes. Yeah. So now electron microscopes, from the name you would not know that they are used to view electrons, see the things that you cannot see, the properties you cannot see with your eyes, right? That's just a quick summary of what these electron microscopes can be used for. Then we have what we know as the particle accelerators. Let's just say if you want to you want to ever work in NASA. Let's just say if you ever want to work in NASA, well, you should also be thanking Marie Curie. If you ever want to do anything that would need the use of radioactivity, yeah, well, you should just be thanking this woman. Every time when you think about it, you say, "Oh, well done, Marie Curie. Such a good great woman," and her work was, I don't know, it leaves me speechless. I don't know what to say. So yeah, you can always find out more, because of course I can't tell you all the fun things that she has done and all the important things that she has done, but you could always check up more on her and see if you actually like what she has done. But whether or not we love it or we do not love it, there's no stopping the fact that it's so amazing what she has done. So that's that for our fun facts in physics for today. So we're going to move to something else. Now let's talk about what do you need to know today. So this class is very short. We talked about what was our last class? In our last class we talked about thermal expansion in solids, and I told you, I put you through linear expansivity, area or superficial expansivity, volume or cubic expansivity. Then we went on to compare density and temperature, right? So we talked about a lot in the last class, and if you have forgotten by any chance, I know it happened, so you could quickly watch that again and come back to this. But for today's class, we're just going to be focused on a short part, and we're just going to explain that, and we're ending the class. Okay, so definition of real expansion, you should be able to give that. And definition of apparent expansion, you should be able to tell us about that. And when anybody walks up to you and says anomalous expansion of water, what's the meaning of anomalous expansion of water? Explain to us. You should also be able to explain, that concept. So those are the three things we're going to focus on, and we'll take one or two examples in the middle. Okay, but we're going to just have a short class for today. So thermal expansion in solids was what we did in the last class. Now we're going to be looking at thermal expansion in liquids. Yeah, thermal expansion in liquids. Solids, liquids, and gases. Those are the states in which matter can exist, right? Which one is your favorite? For once, I want you to think about it. Which one is your favorite? For me, I would say gas. Do you know why? Because they cannot really be easily controlled, or should I not, let me not say control, let me say they cannot easily be held back. They are like they can, yeah, you can contain gases. I'm not saying they cannot be, but they are kind of free. Yeah, I love gases. But solids and liquids is important for us to study them, because you have solids all around in your houses, you have liquids, you drink water every day, right? So there's no running from that. But I love gases. I love gases, and we're going to get to gases soon, and talk about some of the laws and all of that, but that's a story for another day. Let's continue with our topic for today. So thermal expansion in liquids. Now let's start with real expansion. When you hear the word real, if I say something is real in mathematics, when we say numbers are real, it means, okay, you can actually trace these numbers on the plane and on the XYZ plane. You can actually find, grasp them. Like, when we say real numbers, you can say 1 is a real number, 2 is a real number. Now in English language, when you say something is real, it means that thing it actually exists, right? it's not imaginary. It's not something you just came up with or something you just fabricated. It's real. That's the meaning in English. Now when we say real expansion in physics, well, it's a little different, I must confess. So real expansion doesn't necessarily have to do with something comparing imaginary and something that is concrete, but it has to do with taking the totality of something. In this case, now look at this, take a look at this. So real expansion is the actual increase in volume of the liquid per its unit volume per the degree rise in temperature. Is the actual increase. Okay, you're taking into account every form of increase that's going on in that liquid. You're taking into account every form, the vessel, the liquid itself. You're taking into account everything that's going on in that liquid. So real expansion is donated. We already talked about how gamma is used for anything volume expansivity. We talked about how gamma is our symbol. So real expansion here is represented by gamma R. So you can see that gamma R, and apparent expansion is represented by gamma A, and cubic expansion is represented by gamma C. Now, real expansion, like I said, takes into account everything concerning that liquid. It takes into account the apparent expansion, which I would define in the next slide, and it takes into account the cubical expansion of the vessel that actually contains the liquid. For example, you have a cup of water, right? Now, let's assume some way, somehow, that cup of water is subject to expansion, and then the water in the cup expands, the vessel expands. Now, real expansion is such that it takes into account both the expansion of the cup and the expansion of the water. Okay, so by the time we go to apparent expansion, you would see the difference between the two. So if we're to write this out, we would say real expansion equals to apparent expansion plus cubical expansion of the containing vessel. Okay, so let's look at apparent expansion now. Okay, let's talk about apparent. When you say something is apparent, if I say apparent in English language, it could mean a lot of things. It could mean, okay, it's something, it's appearing that this is something is happening. Or if I say it's apparent that you are not interested in this maybe class, I hope that's not true anyway. So if I say it's apparent that you're not interested in this class, it means it appears that you're not interested in this class. Now, when we say apparent expansion of a liquid in physics, we're trying to say that it's not that we're saying it's not real, it's not true, or it's not correct. We're just saying that that is what the expansion appears to be, but it's a camouflage, because the real expansion is not just what the apparent expansion is. The real expansion takes into account more than what the apparent expansion would take into account. Okay, that's why we say apparent. So when we want to define this, in the physics dimension, we would say apparent expansion of a liquid is the increase in volume which appears, now can you say the word appears, which appears to have taken place if no notice of is taken of the expansion of the containing vessel. So the previous example I gave you, I said you have a cup of water, and somehow, some way it expands, and then there's an expansion of the vessel, that's the cup, and there's an expansion of the water inside the cup. Now, if you don't take into account the expansion of the cup, and you just take into account the expansion of the water, that's what apparent expansion is about. You don't take into account the expansion of the containing vessel. Okay, that's what apparent expansion is about. So if you want to get the formula for apparent expansivity, there are two different ways you could do that. You could use the mass of liquid expelled in a scenario where liquid is being expelled after the expansion. You could use mass of liquid expelled over mass of liquid remaining times temperature rise. Okay, but you could also use increase in volume over original volume times temperature rise. Okay, then cubical expansivity of the vessel is 3 alpha. We've already talked about how gamma was related to alpha in our previous class. Okay, yeah, so cubical expansivity is 3 alpha. So now real expansion boils down to gamma A plus 3 alpha. Remember, we said real expansion is apparent expansivity plus cubical expansivity. So now that we know that cubical expansivity is 3 alpha, we could just say gamma R equals gamma A plus 3 alpha. Okay, all right. So I want us to go to an example and see how we could actually use this formula. So for example, this is our question. A density bottle weighed 16.5 grams when empty and 45.2 grams when filled with paraffin at 25 degrees Celsius. When it had been heated to 80 degrees Celsius and cooled again, it weighed 43.5 grams. You have to calculate one, the coefficient of apparent and real expansion. Calculate the coefficient of apparent and real expansion of paraffin. And you should take note that the coefficient of linear expansivity of glass is 0.00000009 per Kelvin. Okay, so what do we do? What do we do here? Now what we're going to do is very easy. What we're going to do here is very easy. So let's start with our solution. First of all, the mass of the bottle is 16.5 grams. The mass of the bottle plus paraffin. Now please take note, the mass of the bottle when it's empty is just 16.5 grams, but when you have paraffin, okay, at 25 degrees Celsius, it was 45.2 grams. Now when the bottle was heated, so mass of the bottle plus paraffin after heating became 43.5 grams. Follow. So now in total, the mass of paraffin that was expelled is the original mass of the bottle plus paraffin at 25 degrees Celsius minus the new mass of the bottle at, after heating has occurred. So 45.2 minus 43.5 will give us the mass of paraffin that has actually been expelled from that bottle. That's one step. Now the next thing is, what's the mass of the paraffin remaining? What's the mass of the paraffin remaining? Now the mass of the paraffin remaining is 43.5 minus 16.5, because you already know that the bottle itself weighs 16.5 grams. Now at the end of the heating process, the mass of the bottle plus paraffin is 43.5. so to get the paraffin alone, the mass of the paraffin that is just alone remaining, you need to subtract the mass of the bottle. So 43.5 minus 16.5 would give us 27 grams. Okay, now the initial temperature of the paraffin when we filled the bottle with paraffin was 25 degrees Celsius. The final temperature was 80 degrees Celsius, and the change in temperature therefore would be 80 minus 25. Okay, 80 minus 25, which is 55 degrees Celsius. Now what next? Let's start with our calculation. Remember this formula. Real expansion is apparent expansion plus 3 alpha. I hope you haven't forgotten. So, but remember that apparent expansion can be calculated using this formula: mass of the liquid expelled over mass of the liquid remaining times temperature rise. Okay. So what's the mass of the liquid expelled? Let's go back and see. Mass of the liquid expelled is over here, 1.7. Okay, what's the mass of the liquid, or paraffin in this case, remaining? Here, 27. And what's the temperature rise? 55. Oh, we're good to go then. We're good to go. So it's very important that when you're solving questions like this, you list out all the known parameters and you list out parameters that you need to know. Okay? It's very, how many times I need to say the very for you to get what I'm saying? It's so important. Okay, so the apparent expansion here would become 1.7 times over 27 times 55. Okay, 1.7 over 27 times 55, and that would give us 0.0011 per Kelvin. Remember that the unit of any type of expansivity, whether linear, cubic, or area, is usually per Kelvin. Okay, remember that. So that's our apparent expansivity. Let's now talk about cubic expansivity. So for cubic expansivity, we're going to do 3 times the coefficient of linear expansivity of glass, and that would give us, 3 alpha, that would give us 0.000027 per Kelvin. Now all we need to do now to get the coefficient of real expansion, what we just need to do is add. We just need to add. So we just need to add, and then when we add that together, we add what we got for the apparent expansion, we add it to what we've gotten for the cubic expansivity. We add them together, and we're going to result. It's going to result in 0.001127 per Kelvin. Okay, it's going to result in that value. So that's our answer for this particular example. Now, if you do not understand it at first, you could pause, rewatch, okay? You don't need to try to get everything at once. Some of us might not get everything at once, but that doesn't make you less of a, I don't know, of a scholar than anyone. So if you're not getting everything at once, you could go back to the start and, you know, try to understand it again. That's the good thing about this video. You could actually pause and, you know, let it sink in. So, and I've always said that if you have further questions on anything, you could just let me know in the comment section. Okay, so let's go on to anomalous expansion of water. Yeah, I like this. Now, okay, let me show you the first statement here. Let's talk about water as a liquid. Now, we've been talking about, look, in our last class, I said this thing, I said a little of it, and I said, okay, I don't want to give you a hint. And I stopped talking. You know, we talked about in the last class how that when temperature increases, it's okay. First of all, temperature is inversely proportional to density. I think we talked about that. If you've forgotten, you need to go back. So we talked about how when temperature increases, density reduces, and when temperature reduces, density increases. But guess what? I love water. It's such an anomaly. But I think sometimes the anomalous things or the anomalous phenomena are actually, should I say, kind of special. So I think water is kind of special. So let's talk about it as a liquid now. Now, generally, we have some properties that liquids obey. You know, at a certain temperature, for the one I just told you about, density and temperature, you know, those are some standard things that should actually happen. But then you see water. It has one kind of special, peculiar behavior between the temperatures of 0 and 4 degrees Celsius. It says, I'm not like every other liquid. No, I'm special. I don't know what other word it uses to qualify itself, but you know, that's what it's telling you. I'm special. So I behave differently. I choose to be different from every other liquid at so and so temperature. So let's talk about this behavior, this, you know, anomaly. So let's talk about that. Now, the anomalous expansion of water is an abnormal property of water whereby it expands instead of contracting when the temperature goes from 4 degrees Celsius to 0 degrees Celsius, and it becomes less dense. Can you see that? So normally, when the temperature is reducing between 4 and 0, normally when temperature is reducing, the liquid is supposed to contract. It's supposed to contract, it's supposed to get smaller. But that's not what happens here. Instead, it expands. So between 4 degrees Celsius to 0 degrees Celsius, when the temperature is dropping from 4 degrees Celsius to 0 degrees Celsius, the water expands and it becomes less dense. That means the density reduces. Normally, the density is, as the temperature is dropping, the density is supposed to increase, right? But water says, no, I'm special. Between 4 and 0 degrees Celsius, when my temperature drops, I do not contract, I expand. I do not become more dense, I become less dense. And yeah, I think water is entitled to make that statement. As I am also entitled, and as you are also entitled to be special. So yeah, let's move on. So I'm going to discuss about this. It's an experiment that was used to actually, you know, talk about the anomalous behavior of water. So we'll talk about that on the next slide. Now, the reason for this abnormality in water is that the water molecules bond together differently between 4 and 0 degrees Celsius, and it's completely different from 4 upwards and from 0 downwards. Okay, so that's the reason for that abnormality, the way the molecules bond. The way the molecules bond. So in chemistry, you would talk about bonding. So you would have an idea of that. Now let's talk about the Hopes experiment. Let's talk about the Hopes experiment. Now, what are the components of this is an experiment that was used, like I said, to talk about the anomalous expansion of water, or the abnormality of this liquid, this special liquid. So this is the setup for the apparatus, the Hopes apparatus. Now, what are the components? First of all, there's a long cylindrical jar. You can see that jar. It's long. This one that goes, and it's like it's shaped in a cylindrical form. That's the long jar, and it's usually filled with water. Okay. Then we have two openings. We have one at the top and one at the bottom. And the reason we have those two openings are to put thermometers, to fit in thermometers. So now we also have a metallic cylindrical airtight trough. That's this one going round. This trough going round is a metallic cylindrical airtight trough, and it's filled with a mixture of freezing mixture of ice and common salt. You know what common salt is? Made up of sodium and chloride and NaCl. Does it ring a bell? Okay, let's move on. So it's filled with a freezing mixture of ice and common salt. Okay, that's what that metallic cylindrical trough is filled with. Now, what happens? How does this prove anything? Now, what happens is that after a period of time, the more dense water, that's the water with more density, collects at the bottom at a temperature of 4 degrees Celsius. Get that? The water that has the higher density, the more dense water, comes down to the bottom at that temperature of 4 degrees Celsius, and that helps us to understand gives us an idea of the anomalous behavior of water. If you're also a student and you have physical classes, and you have the opportunity to actually perform this, get this apparatus, let's assume you actually have that opportunity, you could try it out. You could just have some fun with that and see what you can come up with. So let's just talk about some of the graphs of the expansion. Now look at this. This is the graph of water when comparing density with temperature. Now, as we said normally when the temperature goes from 4 to 0, the density is supposed, since there's a drop in temperature from 4 degrees, we have 4 degrees here and 0 here. Now when there's a temperature drop from 4 to 0, normally density is supposed to increase, because it is inversely proportional to temperature. But you can see it's a sharp drop in the density. It's going down. Okay, so that's the graph of the anomalous behavior in terms of density. Okay, in terms of density. Now let's go to the next one. Okay, we also have ice here. We also have the graph of ice represented here. So let's go to the next one. Look at this volume. We're going to talk about volume now. Now look at the temperature. Between 4 and 0, there is a drop in temperature. There's a drop in temperature between 4 and 0. We know that, right? But look at the volume. What's happening here? The volume is increasing. At 4, the volume here is 1000 cm cube. But as you notice, when it gets to 3, the volume goes up. When it gets to 2, the volume has gone up. When it gets to 1, the volume has gone up. When it gets to 0, the volume has gone up. So it's an abnormal behavior of water. Okay, so that's why we say anomalous. And I think I would use this opportunity to tell you to dare to be different in whatever you find yourself. Dare to be different. Dare to be like water. Dare to be like water. And for the good reasons, please. Okay, so like I said, today's class is really short, and we're done. Yeah, we're done. So that's what we're planning to discuss for today. We went through, we started with real expansion. We talked about apparent expansion. We talked about cubic expansivity when we're talking about real and apparent expansion, and we said real expansion is the apparent expansion plus the cubic expansivity, and then we took an example on that, and then after we took an example on that, we decided to talk about the anomalous expansion of water, and we moved on. We talked about the experiment that we can use to understand it better. And remember, we talked about a woman, Marie Curie. Her name sounds a little like Mercury sometimes. I don't know. I wish I could just say Mercury and everyone would understand. It sounds a little like it. So we talked about her. You could also read more on that. Now, like I always say, and I always say this, you do not just watch videos or listen to your teacher in class or attend a lecture and you just stop there. That's not how it works. Okay, if you want to do better, if you want to be excellent, you need to put in that extra work. Okay, you need to put in that extra work. So I'll give you some questions for today's class, but take note that you should also try to find, some other questions, one or two of them that you could, check out and solve on your own. So these are going to be our questions for today. So I want you to research more on the Hopes experiment. I just give you a little bit of, a background knowledge of what the experiment was about, but you could go further and, just go online and read. Check more about this experiment. It will be fun. If you can't get to take on the experiment physically, you could read more on it. Then you need to solve this question. Try it out, and let me know about the answer in the comment section. If you're able to get the answer, let me have feedback about your correct answer. Then you can play some games on quizzes.com. Also, you can play some games on quizzes.com on expansion if you find that topic. You could also use quizzes.com for other subjects. It's a fun website. Yeah, it's a fun site, and I use it a lot, for some of my games. I make some of my games on it, and it helps a lot. So I believe that today's class was fun. I hope you were able to get one or two important facts. I hope you've been able to internalize some of these things that we've discussed, and I look forward to seeing your comments in the comment section, and I hope you continue to have a lovely day today. Please remember to like the video. You could comment, share it to your friends if you so desire, and please subscribe for weekly updates, regular updates on new topics. Okay, so I'll see you guys again same time next week. Bye bye.